All right, pretty tough exercise this one. We've got 10F, applications of differentiation. And they're applied problems. They are often in exam one. Um, they're often sitting at the end of the exam. And if you do enough of these problems, you'll recognize certain ones come up. Um, this is actually Mr. Tench's advice here. Often you can work out what the solution will be just by thinking about the problem prior to doing any calculations. To maximize the area of a rectangle, it's going to be a square. Okay, so the maximum area of a rectangle is that it will be a square. Maximum area of a triangle, it's got to be an equilateral triangle to maximize the area. Thus, to maximize the area of a triangle, each of the angles must be 60 degrees or pi on 3 radians. So pi on 3, don't know why you actually wrote that in words. A trapezium, this is important, can be maximized using 3 equilateral triangles. So basically, that's our trapezium there. 3 equilateral triangles will maximize the area of a trapezium. Maximize the volume of a rectangular prism, it'll be a cube. Another really important one is this formula here, speed equals distance over time, or the transposed version of that is distance as the subject is speed by time. So let's try to apply it to a few scenarios. This one came up last year from one of my students. It was a really tricky problem. And the way I did it used circular functions, and I had to diff circular functions to get it. But if I had have actually read my own notes, I would have realized that this one here will help me answer this one. So trapezium can be maximized using 3 equilateral triangles. So let's have a look at it. The trapezium, or a trapezium, has side lengths of m as indicated in the diagram below. The maximum area of this trapezium is, okay. So essentially what we're going to do is make it 3 equilateral triangles, noting not to scale, okay? All right, so this is an equilateral, that's an equilateral, and that's an equilateral. That means that's M, that's M, that's M, and that's M. Okay, so the formula for area of a trapezium is area equals half A plus B H. Now, how do I know that? Well, I've got the methods formula sheet actually stuck up on my wall in front of me. That's one of the formulas that you get given. So you don't need to commit that one to memory. So whenever you get a measurement problem on the methods exam, make sure you go and have a look at the formula sheet. It'll be on there somewhere. Okay, so area equals half A plus B multiplied by the height. So area equals half. Let's call this side A, so that's M. Let's call this side B, so that's 2 lots of M, multiplied by the height. Now the height is going to be this height here. Now it's not to scale, so I'm going to draw one of these equilateral triangles, M, 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 and note that the height is actually going to be done using Pythagoras' theorem. Now the height is going to be the square of the hypotenuse, take away the square of the shorter side. Okay, so let's just multiply by the height, which is the square of the hypotenuse, take away the square of the shorter side, which is m squared over 4. Okay, let's keep going on this. So area equals half of 3m multiplied by, now I'm going to put that over 4 and over 4, and that's going to be the square root of 3m squared over 4. Area equals half, well, let's just write that as 3m on 2 multiplied by root 3m on 2. Area equals 3 root 3m squared over 2. just looking quickly at my answers, and that's just a shocking mistake there. 2 times 2 equals 4. So can do all these fancy maths over here and can't multiply 2 and 2 together. So my answer is 3 root 3 m squared, or 3m squared root 3 over 4. There's my answer there. Okay, so this question can be done with circular functions, and you can write an area function using sine and cos, and then diff that function there. But it's actually not necessary if you know these ideas here. And to remember and to use these ideas, you just need to do a whole lot of these questions. All right, next question. Claudia wants to make a rectangular paddock for her pet ponies. She has enough fencing for a perimeter of 400 meters. All right, so we've got y, and the perimeter is 400. Okay, now to maximize, because that's what we're doing, maximizing the area of the paddock, and it's a rectangle, the answer is going to be a square. Okay, so I know the answer is going to be 10,000 already, because it's going to be 100, 100, 100, and 100 to give a perimeter of 400. Then 100 by 100 is going to be 10,000 meters squared. So I know that that's going to be the answer. Okay, but here's how the mathematics actually works. So what I'm going to do is say that 400, the perimeter, equals 2y plus 2x, and I'm going to make an area function. So to do that, I'm going to make y the subject in terms of x. So 2y equals 400, take 2x, y equals 200, take x, and my area, a of x, is given by the length or width, x, multiplied by 200, take x. Okay, so my function is going to have a x-intercept at 0 and 200. It's going to be an inverted parabola. That's not going to be included, but it doesn't say sketch it, so this is just a dodgy job, which means that that value there, 100, the midpoint, is going to maximize the area a of x. Okay, so we're going to say that how are we going to state the dimensions? We don't even have to sort of show all the working out here. So I'm just going to say max area at x equals 100. So the dimensions, length is 100 meters, width is 100 meters, and area equals 100 by 100, which is 10,000 meters squared. All right, so there it is. So no need really for calculus yet, even though we're maximizing things. We really haven't used calculus yet. You could have diffed a of x to get a dash x, let it equal 0. It will come up with x is equal to 100 also, because that's where the stationary point occurs, which then we'd shove back into a of x to get 10,000 as well. What we're essentially going to do is take the idea that we've got this finite amount of surface area, which is, we've got basically 100 centimeters squared of tin or something like that. And what we want to do is work out the largest volume that the tin can be, okay? Given that we can vary the radius, but at most we can make this radius 2 centimeters. All right, so here goes the problem, and it certainly is a good one. Okay, so what I'm going to look at is the total surface area of a cylinder first of all. And I know the curved surface area of a cylinder is actually 2 pi RH. Right, now how do I know that? Well, it's actually on your formula sheet. So again, if you get given these problems, make sure you go have a look at that formula sheet, and invariably it'll be on there somewhere. Now, so that's the total surface area is 2 pi RH, but that's only the curved surface area. So what we need to do is note that in amongst this this badly phrased sentence, we're assuming that it's going to be closed at both ends. So we're going to put 2 pi r squared, which is the area of the ends. Now I know the total surface area is 2 pi h plus 2 pi r squared, so I know it's going to be 100, right? Now, what I want to do is maximize the volume. Okay, so I need to make a volume function. So the volume is equal to, or the volume of a cylinder is equal to pi r squared h. Again, how did I know that? It's on your formula sheet. And what I want to do is vary the radius. Okay, so I'm going to vary the radius. Now it's currently in terms of r and h. What I want to do is knock out the h and make it only in terms of r. So that's why it's important that we got this down. So that tells us that in this formula here, what we're going to do is make h the subject in terms of r and slam it in here, and it will give us this volume function in terms of r only. So let's go ahead and do that. I'm going to go 100 take away 2 pi r squared equals 2 pi r h. H equals 100 take away 2 pi r squared over 2 pi r. Let's see, what we can do is divide by 2 or pull out 2 as a common factor here. H equals 50 take away pi r squared over pi r. So I've cancelled that. 51, 1. Okay, so we're ready to shove this into the volume function. So V equals pi r squared multiplied by 50 take away pi r squared over pi r. Now I can knock out pi, I can knock out one of the r's, which gives me a volume function of 50r take away pi r cubed. Okay, so it's a negative cubic function. So negative cubic functions look like that. And well, like it was already in this form here, but I'm going to refactorize it. 50 take away pi r squared. 0 equals 50 take away pi r squared. So what I'm going to do is get an idea of what it looks like. It's going to have an x-intercept at, or an r-intercept at 0. That's that one there. And 50 take away pi r squared on 2. No, not on 2, equals 0. R squared equals 50 over pi, and r equals plus or minus root 50 over pi. R equals plus or minus. Root 50 is simply root 25, that's 5 root 2 over root pi. Okay, so what is going to happen here? I don't really know what this value is. Can approximate. Let's see how good my approximation is. Root 2 is 1.4. 5 lots of 1.4 is 2. That's like 7. Root of pi is a bit less than 2. 7 over 2 is 3.5. So it's roughly plus or minus 3.5. Right? Let's find out. We've got a calculator here, so let's just do it. So I'm going to define my function first of all. Equals x multiplied by 50 take away shift 0 for pi x squared. Let's have a look at it. Looks good. Let's solve f of x equals 0 for x. And I guess 3.5. How good is my guess? No, not bad. 3.9. Not bad. 3.9. Okay, so this is going to be 3.9. This is going to be negative 3.9, and it's a negative cubic, so it's going to do this. All right, so what we now need to know is the greatest volume it can have if the radius of the tin can be at most 2 centimeters. So the largest value of r that we can use is 2. Okay, now here's a really good problem, because this maximum here, I don't know where it occurs, for what value of r it occurs at. But if it's more than 2, then the maximum over here is going to be what I take as the maximum. I'm not going to say that the radius is 2. I'm not going to change it straight to 2, because that'll mean that, what am I trying to say here? I'm going to do it and try to show you my decision-making process. All right, so I'm going to go back into standard mode, and I'm going to diff f of x, which gives me that. I'm going to solve it. I want to find out what the value, the r value of that stationary point is. Right, so we've got 2, we've got this stationary point and this stationary point. So I want to do f of this value here. And it gives me that. Okay, now we want to know roughly what that volume is there. That's 76. Okay, so the volume at that point there is 76. Right, so let's formalize this a little bit better. So dV dr is equal to, where was it? Negative 3r squared pi plus 50. I've just copied it straight from the calculator, that one there. I'm going to go 0 equals negative 3r squared pi plus 50, and r is equal to plus or minus 5 root 6 over 3 root pi. So now I'm going to sub 5 root 6 over 3 root pi into v. So we're going to say that v equals, or to 2 decimal places in this case, so v equals 76.78. All right, now what we're going to do is compare that to if I just shoved 2 in. So I'm just going to do f of 2, which is the maximum the radius is allowed to be. And ooh, isn't that interesting? So sub r equals 2, v equals 74.87. So if I use this maximum value here, r equals 2, I get this volume. But if I use the local maximum of the function, I get this volume here, okay? And actually, this is the one I want. Okay, now there's a further discussion point here, because where does this maximum occur? It occurs here. All right, so actually we want to explore this part of it in a little bit more detail. Okay, that's very, very interesting. So I've just gone back here and solved, or done the solve in decimal mode, and noted that this maximum occurred when r was equal to 2.30 dot 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 dot. So what happens is, if we look at this part of the graph in a little bit more detail, the maximum occurs at 2.3 to give us 76.78, but prior to that, they're saying that I'm only allowed to use a maximum radius of 2, which is 74.87. So this is our maximum volume. So max vol is 74.87, and it will be centimeters cubed. So extremely tough problem there, because again, if you use a bit of calculus on that, calculus gives you maximums, and the maximum volume according to, you know, everything should be 76.78, but we have this restriction on it, which is 2 centimeters. What would be really interesting is if the question itself asked or said you could have a maximum of, say, like 3, right? Because then that would be at the other side here, which then we would take the maximum value and we wouldn't just put in the highest radius. So that would be an interesting twist to the problem as well, okay? But yeah, pretty tough problem there because the maximum value of the function or the local maximum of the function isn't in fact the one that we're taking. We're taking the one that would be given from the radius equals 2. Okay, the hits keep on coming. This is not an easy one either. Got a swimming pool here, dimensions AB 75 meters, AD is 30. Where's AD? 30. Gabrielle can swim at 1 meter per second, run at this pace, 1 2/3 meters per second. She starts at A, swims over to here, so this is the swim leg, and then runs from P to C. She takes 2 seconds to get out of the pool. Let dP equal x, the total time taken to be t seconds. So here's something we need to know. Speed equals distance over time. Okay, so what we want to do is work out the time taken. So time is equal to distance over speed. So what we're going to do is work out this distance here and throw it over the speed, plus we're going to work out this distance here and throw it over the speed of that leg there. Okay, so the time for this leg here, well, this is just going to be, so I want to work out the distance AP. So AP is given by, this is just Pythagoras' theorem, and we've got the two, we need the hypotenuse, so we just add the shorter sides together, so it's going to be root 900 plus x squared, or that there, so that's a good sign. So I'm just going to write it in here. To show that, so I probably should do a bit more working. So 30x AP equals 30, or AP all squared equals 30 squared plus x squared. AP equals square root of, I've got to do plus or minus if I'm doing this, 900 plus x squared, but AP greater than 0, therefore AP is equal to 900 plus x squared. So that's the distance there, 900 plus x squared over the speed, which was 1 meter per second, so over 1, plus this distance here, PC, which is going to be 75 take away x, over the time it took her to do that, which is 1 2/3, or 1 3s are 3, over 5 on 3, plus it took her 2 seconds to get out of the pool. T is equal to 900 plus x squared over 1, so I'm just going to forget that happened. This is going to be 5, divide by 5 on 3 is the same as multiplying by 3 on 5, so that's going to be 3, 75 take x over 5 plus 2. How's it written? They've got it as that, so t equals as required. Okay, so all right, on to the next problem. All right, this corker was written by Mrs. Brown back in 2016. Yeah, it's a really common style of problem. I'm going to show you two ways of doing it. One is the hard way, and one is the easy way. What am I going to go for first? Let's do the easy way first. All right, so P is a point on the line 2x plus y equals 6, such that the length of the line segment OP from P to the origin is a minimum length. So P is some sort of a point on this line. So let's try to visualize it. So that's going to be y equals negative 2x plus 6. So it's 6, it's got a negative gradient. P is a point such the length of the line is minimum length. Okay, so there's a thing you need to know about minimum length. And the thing is, if you've got a linear function, then the minimum length is always going to be perpendicular to the line to go through a particular point. In this case, it's the origin. So OP is going to be, no, that's going to be P and O. So that's what we're after here. So basically, here's the strategy. This line here is y equals negative 2x plus 6. This line here, we can get the function. It's going to be, so recall perpendicular lines have a gradient which is the negative reciprocal of the original function. So this is going to have a gradient of 1 over 2x. And because it goes through the origin, it's just going to be plus 0. Now what I'm going to do is let these equal each other, and that's going to give us the x value for where this occurs, then slam it into one of them to get the y value, and we've got the point on the line that causes the minimum length of this line here to go through the origin. Okay, so we're going to say that negative 2x plus 6 is equal to x on 2. I'm going to multiply everything by 2. Negative 4x plus 12 equals x. 12 equals 5x. X equals 12 on 5. All right, and what I'll do is I'll just sub that. Sub x equals 12 on 5. And I'm going to sub it into this one here. So y equals 12 on 5 cut in half, which is 12 on 10, which is 6 on 5. So the coordinates of the minimum distance is going to be 12 on 5, comma, 6 on 5. All right, that is the easy way. All right, here's the hard way. All right, so what we're going to do for the hard way is to work out, we're going to use the idea that the distance between 2 points, we're going to get the distance between 2 points here. So one of the points is 0, 0. The other point is x, and the y value is simply going to be negative 2x plus 6. Okay, for that particular value of x, this is going to be the y value. So what I'm going to get is a distance function here, and I'm going to minimize the function so that I can get, what am I going to get? The minimum distance from this line here to the origin. So it's going to be the difference between these two. So it's going to be x squared take away plus rather negative 2x plus 6 all squared. So simply just Pythagoras' theorem. Distance equals take away 24, what is it, 24x plus 36. Make sure you extend that root sign out. D equals 5x squared, take 24x plus 36. All right, so now what I've got to do is diff that thing. All right, so it's going to be chain rule. So I'm going to do dd dx equals. So to do chain rule on this, it's just going to be d equals u to the half, u equals 5x squared, take 24x plus 36. So it's going to be half u, which is going to be 5x squared, take 24x plus 36 to the negative half, multiplied by the derivative here, which is 10x take 24. Okay, so that's going to go in the numerator, in the denominator. Oh, this is brutal. Okay, 10x take 24 over 2, 5x squared take 24x plus 36 to the half. Make sure you extend that vinculum across. 1, 5, 12. Oop, I can sense it coming here. All right, so now I'm going to say dd dx is equal to 5x take 12 all over this thing here, root 5x squared take 24x plus 36. Now, the maximum occurs when that's equal to 0. 5x take 12 over 5x squared take 24x plus 36. Right, so that gets knocked out. 0 equals 5x take 12, x equals 12 on 5, and then I'm going to sub that into this one here, because I kind of don't know the second function. This is presuming I don't know that it occurs at a line or for a line perpendicular. So sub it into that one there. So y equals negative 2x plus 6, y equals negative 2 times 12 on 5 plus 6, y equals negative 24 on 5 plus 30 on 5, y equals 6 on 5. There we go. So the coordinates of the minimum distance that will cause the minimum distance is 12 on 5, 6 on 5. There you go. Same answers. This one is a lot more problematic. That one is easy. Okay, so you want to use that technique rather than that technique, but many students will use that because they're just mad for calculus. All right, this one here is another really tricky problem. So it costs 12 plus 0.008 x dollars per k to operate a truck at x k's an hour. In addition, 14.40 per hour to pay the driver. Okay, so what we want to get is the total cost per k if the truck is driven at 40 k's an hour and 64 k's an hour. Okay, well, the cost per kilometre, it costs this much per kilometre to operate a truck at x k's an hour. So it's going to be 12 plus 0.008 multiplied by 40 plus 14.40 per hour to pay the driver. Okay, now 14.40 per hour. Okay, now what that means is we know that in 40, it does 40 kilometers per 1 hour. Okay, or let's divide that by 40 and divide that by 40. It does 1 kilometer per 1 over 40 hours. Okay, so costs 14.40 per hour to pay the driver. Okay, so that then represents the time fraction of what it takes. So we're going to do 14.40 multiplied by 1 over 40. So the cost is going to be, and let's just pump this into the calc, 12 plus 0.008 times 40 plus 1440, and get the time fraction there. So the cost is going to be 1268 per kilometre. So the total cost per kilometre, if the truck is driven at 40 k's an hour, is $12.68. Seems expensive. Anyway, right. This is a 1. Now let's do 2. So it's going to be similar. 12 plus 0.008 multiplied by 64 plus 1440 times 1 over 64. Okay, now let's change that on the calc. 64. So, as I'd expect, 74. It costs a little more if you drive the truck faster, or it doesn't offset the costs per hour. So that's going to be the cost there. Okay, write an expression C. So let's do B. C equals cost per kilometre in terms of X. All right, so that's going to be 12 plus 0.008 times X plus 1440 times 1 over, and instead of the speed being known, we don't know how fast they're driving. Let's clean it up. 12 plus 0.008 X plus 1440 over X. Okay, sketch the graph of C against X for 0 to 120. Okay, so here's how this one's going to work. So we're going to have X and cost. And what's going to happen is if the truck driver drives the truck really slow, like 1k an hour, it's going to cost a lot of money because, like, if you look at it, right, like if this is our function, where is it over here? Our function's here. So if it's really slow, you can imagine a small number going into 1440. What it's going to do is it's going to make this massive, i.e. the cost is going to increase astronomically if the truck drives really slow because the driver's going to get paid a bucket load. Never mind the fact that this is small, that kind of is negligible there. And it becomes a little bit, shall we say, a little bit like hyperbolic, right? Now what's going to happen is, so it'll be like infinity, and it's going to come down to a minimum point, and then what's going to happen is the cost is going to increase again. Okay, so it's going to come back up again. Now, why is it going to do that? Because even though you get there really quickly, what's going to happen is the higher the speed, the more it costs to drive the truck. Again, in terms of, I don't know what damage you do to the truck. I don't know. I'm no automotive expert or anything like that. That's what's going to happen. It's going to increase. Right, so what we need to do is find out what the cost is when that happens. So to do that, what I'm going to do is just use some calculus to get that. So I'm going to define f of x as the cost function, which is 12 plus 0.008 x plus 1440 over x. I'm going to diff it, solve it, let's get an exact out of it, solve answer equals 0 for x, and I've got 2 points there. Why do I get 2 points? Negative. Well, we're going to assume that x is greater than 0 and only take the positive anyway. So that's going to happen at 30 root 2. Now we're going to put that into the cost function. So f of 30 root 2, which is that. Let's get an approximation. 12. Seems really low. Okay, so the minimum cost here, that's all right. So 12.668. So that's the minimum cost will be $12.68 per kilometre, and then it's going to increase. Now, here's so we're going to this function here. I'm going to call it a freaky function because you haven't seen one like it yet. So what happens with this function here is as x continues to increase, the bigger and bigger x gets, what it's going to do is, you imagine this number here, 1440 over a larger number or a really large number, this fraction is going to get smaller and smaller and smaller and smaller and smaller and smaller. Okay, so the first thing I'm going to do is just get f of 120, which is 1308. All right, so it's going to increase back up here to this point here because they want it graphed. Is that what I'm doing? Yeah, sketch the graph between 120. But the really interesting thing that happens with this function here is actually it starts to asymptote along this line here. Y equals 12 plus 0.008x. Now, why is that? Well, what happens is the cost keeps increasing, but as x gets larger and larger, this basically is negligible because this number here, 1440 over an extremely large number, will just be 0. Okay, so it just tends towards this asymptote here and will just basically behave like the linear function. The function is just going to behave linear from here on because this part of the fact that we've got this driver fee here, it's negligible because it tends towards 0. So there's our graph there, and at what speed should they drive at? Well, it's just the minimum, which was so at what speed? It was back here, 30 root 2. And we'll just approximate 30 root 2. So x is equal to 30 root 2 or 42 point, it doesn't say to approximate, but 43 kilometers per hour. So that's going to be the rate in which the truck should be driven to minimize the total cost per K. Okay, so yeah, pretty tough problem. Go through that one a few times because that's tricky. Okay, last problem. It's believed that for some time after planting in ideal conditions, the area covered by a particular species of ground cover plant has a rate of increase. Whoa, that's cheeky. All right, so underline that, okay, of y centimeter squared per week given by this function here, where t is the number of weeks after planting. All right, so we'll talk about this in a sec, but this one here is going to be a basic find b and c using the table of observation. So after 1 week, the rate of increase was 10 centimeter squared per week, and after 2 weeks, the rate of increase was 24 centimeter squared per week. Okay, so we're going to say that 10 equals -1 plus b plus c. So just subbing 1 in and 10 in. 24 equals -8 plus 4b plus 2c. 11 equals b plus c. 32 equals 4b plus 2c. 22 equals 2b plus 2c, 1, 2, and let's do 1, take away 2, 10 equals 2b, b equals 5, c equals 6. Therefore, y equals negative t cubed plus 5t squared plus 6t. Okay, assume that the model is accurate for the first 8 weeks after planting. When during this period is the area covered by the plant a maximum? All right, so what we need to know here to do this problem is that y is actually the rate of increase. So it's already the rate, okay? So let's have a think about how this works. So we're going to go y equals negative t, t squared, take 5t, take 6. That's going to be negative t, 6, 1, tt, negative t take 6, t plus 1. So we're going to have 1 there, negative 1 and 6, and it's a negative cubic, so it's going to look like that. Okay, so this is going to be the rate versus time. Okay, now where do we go with this one? Okay, so when is the area covered by the plant a maximum? Well, this looks like it's the maximum here, but actually this is when the rate of increase in area is at a maximum. So if you chose that point there, what you'd be actually answering is this question here, okay? To do this one here, what we've got to think of is what would the original graph look like, which is area v time. And what this actually would represent is the change in area over time. So this is actually, the way to think about this is actually the gradient graph. And what would the original graph actually look like? Well, let's have a think about that. Okay, so what we've got is stationary point, and stationary point. Okay, so we've got a stationary point somewhere here, a stationary point somewhere along, so somewhere along this line, somewhere along this line, and somewhere along this line here. Okay, now let's have a look. What's happening here? We've got a positive gradient, then a negative gradient, negative gradient, then a positive, then a negative gradient. So how are we going to draw this? So the first thing I'm going to do is draw a positive gradient, okay? And then we're going to get a stationary point. Then we're going to get a negative gradient through to the next stationary point. All right, then what we're going to get is a positive gradient. I've got myself confused there. So we've got negative gradient to the stationary point. Oh, pausing. All right, so we've got our positive gradient here, so that's our matching positive gradient there. We've got our negative gradient here, that's our negative gradient here, through to this stationary point. Now, I'm presuming this stationary point is when t is equal 0 and area is 0, because I presume that they've just been planted. I believe that for some time after planting, in ideal conditions, the area covered, so they've been planted at time 0, so I presume that that is the area covered at the time of planting is 0 or close to 0. And then note here that we've got a positive gradient all the way through to the stationary point at 6. So we're going to have a positive gradient through to a 0 gradient point, and then we're going to have a negative gradient. So that's basically what my area function will look like. And if you notice here that the maximum area occurs when, at this point here, when t equals 6. So the area covered by the plant as a maximum is at t equals 6. Right, that's very difficult, and to do this, what you want to do is just go back to this function here and consider what it is, which is it's a rate. Read these questions really carefully. So if you've got this rate here, then what you do is this basically is talking about what the original graph was, okay? The area covered is the original because when I diff area v time, I get the rate of change in area versus time, okay? So that's kind of like the derivative graph for the area graph, okay? That's the way I try to think about it. Right, so it must have occurred when time is equal to 6, okay? But obviously couldn't be negative. Time couldn't be negative anyway, so this part here is not important. Okay, so then the second part says, when is the rate of increase in area a maximum? Well, that's just going to be this point here. So what I'm going to do, I'm just going to do this last part. Should I do it on the calc? No. So that's the answer to part 1. So part 2, when is the rate of increase in area the maximum? We're going to go dy dx equals negative 3t squared plus 10t plus 6. So we're going to 0 equals negative 3t squared plus 10t plus 6. We're going to say that t equals plus or minus root 43 over 3 plus 5 over 3. But t greater than 0, so t is equal to root 43 on 3 plus 5 on 3, or more realistically, or after 3.852 weeks. Okay, should have specified an approximation, but that's the exact amount of time. So that's this point here, that's 3.8 to get the maximum rate, whatever the maximum rate is. Okay, it doesn't really matter, it doesn't ask for that. They just want to know when the rate of increase in area is a maximum. That's after 3.852 weeks. Right, so again, really tough problem. There was one actually like it on the SAC last year that was a little bit of a shambles. So make sure you do have a good long look at this question here and work hard on it.